so you need to re-register. So tonight's talk is Drought, Paleoclimate, and Dust. And 2 weeks from tonight, on May 11th, we'll have Deb Horde, president of Photosynthesis Production, talking about making science film. On Tuesday, May 16th, we'll have a special educator event with Dr. Marianne Krasny talking about her new book. On the following night, Wednesday the 17th, we'll have a session on feedback on the changes for the climate literacy principles. And our last session of the year will be May 25th, talking about the electric grid and the necessary changes there. And now I am going to skitter ahead to tonight's slide and hand it off to Toby, who is joined by Carlos and Frank. And I'm going to say, take it away, team.
Great, thank you. And thanks everybody for showing up. I will try to keep my comments pretty quick so that we can spend more time on the people and my broader research group, Frank and Carlos, who are doing much more of the cutting edge, exciting science and have some fairly recent new results to share and to discuss. But I wanted to just do a real quick overview of some key concepts and ideas that we tend to think about when we talk about drought. So what are we talking about when we talk about drought? And it's a small enough group. I mean, can everybody use the chat? Is that work done?
Yes, it does.
All right, cool. So I'll open up the chat, and if everyone just puts down in the chat like the first 2 or 3 words that come to mind when you hear drought, I'll take a look at it and weave it into my next few slides. So it's just the first, just put in the chat first few words. Dry, yeah. Arid, yes. Mud cracks, moistureless. That's the mud cracks, a nice vivid image of what the drought looks like. Dying plants, irrigation, dust. Yeah. Anyone else wants to contribute? Go for it. All right, I think we will. Oh, nice one, Brendan. Dry, climate change, agriculture. Yeah, so this is great because drought tends to mean something different to almost everyone, and it's a phenomena that's very application and user specific and ecosystem specific. And if you're, a grower in upstate New York and you have an apple orchard, the threshold for what counts as drought to you is maybe different from if you're a corn farmer in upstate New York on the plot next to the apple grower. The threshold and what constitutes drought could be different because you're more sensitive to that, short window in the middle of summer when, if it's dry in, say, July, it hurts your crops. Whereas if, you're an apple grower, you maybe have some more tolerance because the root zone of those apple trees goes deeper into the soil profile of the earth. So what I want to talk about sort of briefly is that when we think about drought, we tend to divide it into a few different categories. They're loosely thought of in terms of their duration. So there's meteorological drought. Usually we talk about meteorological drought. We're talking about weeks or months. In some regions, you think about a really hot, maybe a tropical region like the Caribbean or parts of Southeast Asia. A dry week in the middle of the wet season, when you're supposed to get those monsoon rains, the beginning of the monsoon season, that can be really damaging for agriculture, for ecosystems as well. This is from a trip I was on in 2012 to the Midwest. There's a big drought in the summer of the 2012 in the Midwest. Agricultural drought we tend to think of as being more like months, seasons. It starts to affect agriculture. There's a picture I took from backpacking trip I went on with my sister a few years ago in Washington, the Western US. That's Mount Adams in the Cascade Range, and the whole region has just been devastated. This part of the forest has been devastated by big wildfires that followed prolonged droughts, and that's a longer time scale. Still, And because we're humans and we use water in all kinds of different creative ways, we have to think about and worry about could be called hydrological drought. So reservoir levels getting low, that probably occurs on timescales of seasons, years, even decades, especially if you've been following the news about drought in the Western US. And then, to sort of close the circle, and this is always going to be an important thing to think about when thinking about drought, is the socioeconomic element of drought now more than ever, I would say, is an important consideration, because we use water and we move water and we pay for crops, or we pay for products that require water in different ways. And so it's a vastly more complicated, coupled socioeconomic environmental system than it would have been even just a few generations ago. I'm not going to spend a ton more time on how we monitor. I think this is going to be talked about a little bit in the subsequent talks today, but I do want to point out this product called the US Drought Monitor. And this is just a screenshot from a few years ago where you can see there's a subjective element already built into one of the primary tools that's used for monitoring drought. And the subjective nature of this product, which, basically drought managers call around the country to different counties and ask people what they're observing on the ground and have them report back what they're seeing and put it together to produce the drought monitor. That subjective nature is usually really fundamental to any understanding or any research into drought. And this makes it a very challenging and very interesting problem, because unlike temperature, you can just go out and measure temperature directly. Well, we'll just say that you can do that. I know there's some complexities of doing it, but you have a thermometer, you can measure temperature. And the thing that you care about, temperature, surface air temperature, is the thing that you're measuring. Drought is different because the phenomena itself is somewhat subjective. And the way that we monitor it is different from how we would measure soil moisture. We could go out and measure soil moisture, not directly necessarily. I'd have to put a soil moisture probe that measures capacitance of the soil moisture column. But even then, it's still not as clear cut that a small sample of soil moisture at 10 centimeters or 30 centimeters is going to indicate drought conditions across larger spatial scales. Differences in soil types, differences in the ecosystem where you're making the measurements, differences in the slope and the runoff rates, all kinds of little small variations in the land surface can make it much more difficult to measure drought directly. Whereas with temperature, tends to, if you have a few sensors, temperature measurements set up across a state or across a county, you have a pretty good estimate of what the average temperature in that region would have been. So it's a hard problem. We're getting to the point where we are making just incredible new high resolution and relatively long temporal coverage measurements with satellite remote sensing observations. Satellites that circle the Earth and they'll sample soil moisture. You can think of it as like, you can imagine if you could just look at the Earth's surface and filter out everything except for the moisture that's in the plants and in this top layer of the soils. That's all you can see. That's like what the satellites are seeing. It was very exciting, very fast evolving time in drought research right now. But unfortunately, these satellite products, they don't have a lot of depth. They don't have a long time horizon. Usually most of these missions have only been around for less than 10 years. And that doesn't give us the broad, long time scales that we'd like to have to understand natural variability in the context of climate change. You can ask if we can model it. This is work that Carlos works on and has done. It requires one of our major tools for climate science, which are supercomputers and global climate models. It's not the same as having measurements, but it's sometimes a good approximation to what those measurements would be if we could have measurements everywhere in the globe. And these slides got scrambled, but let me just end here. I'll stop here and turn it over to Frank, who's going to talk about his work on drought and dust in the Southwest, and I'll introduce his work in just a second. But I want to end here because this is an experiment from a few years ago, one that I've been involved in, work that I published on, where if you look at an ensemble, so a series of climate model runs that were done with a single climate model simulation, single climate model, one that happens to be operated by the National Center for Atmospheric Research. They ran the model many, many times during climate change projection, a business as usual scenario. And what they found was that precipitation over this period in the Southwest increases a little bit on average. The total average precipitation increases a little bit, and the variance in precipitation increases a little bit in the Southwest over this long, this projection into the future. But the soil moisture itself actually decreases, paradoxically, it would seem. And the reason for this is that we have to think about the seasonality of what's happening here. So in the Southwest, which is where Frank is now and is going to talk about, in the Southwestern US, most of the moisture comes in the winter months in the spring, and most of the drying happens during the summer months when there's really high evapotranspiration and soil moisture is leaving the ground because it's hotter. As it gets hotter still because of climate change, that evapotranspiration demand just increases. If you think of it as like a supply and demand problem, the supply side is increasing a little bit during climate change, but the demand is increasing a lot more. And that makes droughts of all time scales apparently much more likely in the Southwest. Now, in the Northeast, and we're going to talk about this a little bit, it's a little bit of a different story, but these same considerations, these same factors, these same limitations, and these same tools all come into play when we think about drought, dust, and climate variations on timescales, longer than a few seasons or a few years. So with that, Frank, I'll turn it over to you. You can share?
Yeah, I can share. Thank you,
I'll stop
Toby.
my share. So Frank I'll just introduce you while you set up here. So Frank is a PhD student that's working with my lab. He's actually at Northern Arizona University working with Dr. Nick McKay, with whom I went to graduate school. We have a collaborative project to look at dust, drought connections and really try to tackle some of the underlying assumptions and paradigms for how drought and dust in the US Southwest are coupled and how they've worked through the years. He's got some really cool, new, exciting paleoclimate results to share. So take it away, Frank.
Yeah, I hope everyone can hear me, right? I hope, okay, great. So this is call it the NAU Cornell Dust Project. So I have it's in 3 parts. So you got the paleolimnology, modern dust, and then the education outreach component. So those are the 3 components for the project. So I'm Franklin Tranquilino Tellez. So I'm a member of Gianade, Nation of New Mexico, a band of Chiricahua Apache. But I was born and raised in Los Angeles, California. I'm a diaspora native. That means that our people were forcefully removed from our homeland. And so some of my motivations, because part of my homeland is the White Sands, New Mexico, and there's a lot of dust there. And my life, Kayaniskatsi, which means crazy life in the Hopi language. I got my Bachelor of Science from UCLA. And then I went to Cal State University Northridge, just up the road, and I got a master's in geology. And then I started working as a freeway flyer, working at various community colleges. I also became a docent at the Natural History Museum of LA County. And then I joined the Navy as a meteorology and oceanography officer in the US Navy Reserve. And then I know it's a lot of stuff here, but and then I went to New York City and I earned a Master's of Arts in Teaching Earth Science at the American Museum of Natural History. That's where I learned a lot of the pedagogy, andragogy of teaching science. And now I'm a PhD student here at Northern Arizona University, learning about dust and mega droughts and pluvials and mega pluvials, fun stuff. So that's this is the outline for today for my presentation. And so motivation, Columbine Lake varves. What are varves? Modern dust trap network. I created a website, curriculum development for schools, and what are the next steps? So part of my motivation comes from working in New York City. And I was a graduate student there at the American Museum of Natural History, collecting micrometeorites, trying to look for micrometeorites in the dust of urban rooftops, but didn't find any. And then I taught at Harlem Renaissance High School in New York City, in Manhattan. And so here at NAU, I'm looking at Columbine Lake Varve. So that's about 600 miles northeast of Flagstaff in Colorado, southern Colorado, in the Colorado Rockies. So some of the research questions I'm trying to answer here is, when is dust accumulation most prevalent? during a prolonged drought, during a pluvial cycle, during a drought after a pluvial, during a pluvial after a drought? What are the dust flux comparisons and contrasts? So a varv or varves is just layers of mud that are deposited in a lake. And it's just like tree rings. Every year you get a layer of dust per se. So I'm looking at the last 2,000 years. So here focusing on the last 1,500 years. And the question here is, what was responsible for the increase in dust variation? So I use an ensemble in R language in coding. So, and it measures the thickness of the varves. So that was a previous student, Stephanie Arcusa, who did that. And I'm just continuing her work and with higher resolution. So we're looking at these varve results. And so you could see that in the mid 1500s, the history tells us that in the mid 1500s, the Spaniards, conquistadors, were looking for gold in the US Southwest. And then in 1680, there was a Pueblo revolt, thanks to Popeye, Tewa leader. And then in the 1690s, the Spanish sent Father Eusebio Francisco Quino, who encouraged European agriculture and ranching practices, introduced exotic species of cow, sheep to the settlers and indigenous communities in the area, which kind of destroyed the protective cover of the fragile landscape. And then in the mid 1800s, with the idea of manifest destiny, Homestead Act encouraged settling of the West with the Homestead Act of 1862. And then the Pacific Railway of 1862 encouraged the building of the railroads. And then the General Mining Act of 1872, the Desert Land Act of 1877 generates a lot of dust. As you can see here, you can see that prior to the 1690s, there's kind of stable dust in the Columbine Lake Vars, but starting around the 1690s, there's it kind of the variation goes crazy after that. So here I'm trying to connect the PDSI, or the Palmer Drought Severity Index, which is a proxy for soil moisture. So I focus on Arizona, and the reason why I focus on Arizona is because it's upwind from the study area in southern Colorado. So the wind goes towards the northeast. And so I'm trying to connect the Palmer Drought Severity Index, which comes from the North American Drought Atlas, the NADA network. So that's the website. You can download the data. It's where I download and try to correlate that to the dust. As you can see here around 1690s, that's when the dust flux kind of increases. But we're also looking at prior to in the first millennium, from the first 1,000 years and then the second 1,000 years. The correlation here is on the right. You can see the correlation analysis here from for the last 2,000 years. You can see that just recently, you can see that negative correlation there. And then focusing on the 20th century, you can actually see the negative correlation here between the soil moisture proxy, the Palmer Drought Severity Index, and the dust flux. You could see that at the beginning of the 20th century, we had a pluvial from 1905 to 1917. That's where the PDSA is above zero. That's wet. Below zero, that's dry. So at the beginning of the 20th century, it was wet. And then in 1929, it started getting dry. And so between 1929 and 1940, that's known as the Dust Bowl. You remember that from history class. And then in the 1950s, you got another drought there, the 1950s drought. So that contributed a lot of dust into the Columbine varves, the Columbine Lake varves. So here's a reconstruction between soil moisture and dust flux, looking at the first 1,000 years and the second 1,000 years. So there was an extreme drought event in the 2nd century that lasted 80 years. So between 202 to 282 Common Era, that's an 80-year drought, continuous drought. That's the worst drought in 2,000 years. So I'm going to be looking at that. And then, but if we look at the late 1600s, you can see that the dust flux kind of just goes crazy. The variations just increase. So this is the second look. I was just looking at the 2nd century here, the results for the 2nd century mega drought. You want to call it that, yes, because it's more than 20 years. That's a mega drought. So VAR results, these are the density plots, comparing drought years to non-drought years, and then wet years to non-wet years. So these are the density plots to compare what's significant here. And it seems to me that the first, the 1000 to 2000 Common Era, the normal years are more significant, but not too much more significant than the dry years or the blue years. The blue years won't even show up here. And then, so that's the paleolimnology. So I'm continuing doing that work. So the modern dust survey includes dust traps. So you can see the dust traps here. The dust traps, it's after the methodology that was established by Meredith Rees out of the USGS in Denver, Colorado. So I'm in contact with her, and she has shown me her methodology. As I'm in email correspondence with her, and she has sent me some of these, well, not some of the pictures, but she sent me her resource, and then I took pictures of my dust traps that I'm putting around Flagstaff. So the dust traps start out at Camp Verde, and they go all the way up to Soap Creek. So I'm covering a transect of 245 kilometers from Camp Verde to the south, and then Soap Creek or Marble Creek to the north of here. So that's 245 kilometers of transect. Right now, I have 5 active dust traps, unfortunately, but soon I will have more. I went out today, just prior to this meeting, I went out to just south of here to post another dust trap. So we have 6 of them now. I'm also collecting a snow survey, collecting dust on snow. So I've been doing that too. So I collected dust from O'Neill Crater, Strawberry Crater, Sunset Crater, Eldon Mountain nearby in Flagstaff. And then I'm going to go up to one of the San Francisco peaks this Sunday to collect some dust on snow, because they're good receptors for dust. That's what I'm trying to get here. And I also created a website. So this is the third part of my project is education outreach, public outreach. So this is the website that you can actually click on, or you can use your phone and use the QR code. It'll take you to the website, and I update it weekly or 3 times a week. And so I add things to that. And here you can see my advisor, Nick McKay, Stephanie Arcuza, who completed the first phase of this project. And so the third part of my project is discipline-based education research, or geoscience education research. So I'm creating a curriculum, dust curriculum, that's aligned to local ecological knowledge or traditional ecological knowledge, TEK, aligned to state standards in Arizona, the next generation science standards, and hopefully when I'm in New York, use the New York State standards for Earth and space science, because hasn't been implemented yet. But I'm familiar with the Earth science reference tables, because I've used them and used the phenomenon place-based education, student-centered, and the 5E, BIBE, engage, explore, explain, elaborate, and evaluate. So all of those things combined. And this is a test run for my education outreach. It's a Saturday Academy through the Institute for Tribal Education Professionals. So I tested this out with Hopi students and Navajo students. So if you want a copy of this, you can go to the website. You do have access to these lesson plans, these worksheets. So one of the lessons here is an engage lesson. And then that's the dust hunt, so that students can collect dust using tape, using magnets, and then one of the other ones is the role of wind on dust. So using boxes. So let me see, it's not here. I didn't put it in there, but using boxes to simulate dust storms. So using a hair dryer, putting a hole there, using soil types fine-grained sediment that's local to the area and generating a dust storm. And then also using forks as stabilizing, as simulating vegetation. So using those physical models to engage students. And then using maps to pinpoint hotspots. Where are those hotspots of dust on Google Earth? And so some of the evaluation from that, I have 3 teacher evaluations. And as you can see here, what did you like most about the session? Each session is always informative. Students enjoyed their class, asking questions, that the students were engaged, they had fun. Do you have any recommendations for improvements? Doing awesome, thank you. So that was evaluation from the Shanto Preparatory School on the Navajo Nation. And then from the students, 17 students, tell us something that you learned in this session. I learned how dust is good. Well, not all dust is bad, because we need dust to create cloud condensation nuclei to generate precipitation. So that was one of the lessons, was to generate cloud in a bottle. I don't know if you've ever done cloud in a bottle, but it's just one of those things that students get engaged in. One of the other things I learned, that the Navajos have been having low rain, and they wanted to have more rain so they would grow. And then sand and wind make sandstorms. I learned from this session is dust storms make out of sand, dust, and wind. How to make dust clouds using the physical models. And so these are all the various sentences that the students wrote down on the evaluation sheets after completed the Saturday Academy, the 3-hour Saturday Academy, a few months ago already, March 25th. And so the next steps is to set up more dust traps. My objective is to have 17 of them. Continue working on the Columbine Lake VARs and draft an outline, complete the dust curriculum, and reach out to the schools via the Institute for Tribal Environmental Professionals and the Arizona State Parks. And also I already have, I didn't put that here, but I created a graph where you could see that the cow, there's an increase of cows. There's millions of cows in Arizona, and that's generating a lot of dust in the area. And also prepare for fall 2023. My hope is to be at Cornell to collaborate on the dust project there, and go on the wind tunnel and see what's there. So I appreciate your attention. I don't think that's I believe the last slide. So that's my presentation here. Appreciate your time. Thank you.
Thank you, Frank. No, it's really exciting to see. And Frank, it doesn't seem this way. It always surprises me, but you're a relatively recent enrollee in a PhD program. You've done an amazing amount of work, but it's only been like 2 years, right?
Yeah, so just 2 years. That's it.
Yeah, not even 2 years actually, right? So you started,
Yeah.
So it's really an impressive body of work already that you're generating, and it's such an important perspective, and one that I always am reminded of when I talk with you and Nick and other people who work in the paleoclimate world, that like our little snapshot of 50 years or 100 years, whatever you want to call it, of like, relatively high quality instrumental records of temperature and precipitation. It's just a little snapshot of the full range of possible dynamics that are already in the system and that we have records for, and that we have, histories that could help us understand better. So thank you, Frank. And now I'm going to turn it over to Carlos, who is the most senior research scientist in my lab and is just like the engine and jack of all trades that makes all of us able to like get things done. And we appreciate him immensely. He has been doing some of the, I would say, most cutting edge research of any group that I know of on the predictability of drought and drought dynamics, focused on the Northeast. And like me, he also has a University of Arizona connection. He did a PhD at the University of Arizona, as did I. So we've got this cross-continental view of drought. And I think, Carlos, you would probably agree that drought dynamics and understanding drought in the Northeast is in many ways harder than in like the Southwest and the Western US. Maybe not in all ways, but in some ways. It's certainly harder, and it's certainly less well developed. So take it away, Carlos, talk about your work.
Thank you very much, Toby, and everyone for allowing me to talk today about something that has been my passion for the last maybe 10 years already. I graduated from the University of Arizona, where I started studying a multi-year variability of drought. And since then, I didn't stop until now, where I'm going to try to show our most recent work about droughts in more specifically predictability of drought. And the figure here at the bottom show an example of the 1916 drought. And there we are using the Palme Drought Severity Index. And in the next slide, I'm going to just say PDSI for short. And here the color show in brown the intensity of drought most focused on New York and Pennsylvania. The data is local, it's from the Northeast Regional Climate Center. So we are always working with local information, and we see what is interesting I had to show today. So this question he asked, and I say asked because that included Toby, and is one researcher at Cornell, and he asked me directly, "Hey Carlos, how predictable are droughts?" And that happened when I just arrived to Cornell, 2016, and we are having a very interesting case of drought. So the question was posted, like I put it in this paper who was published last year. How predictable are short-term droughts in the Northeast United States? And this was in a like group meeting, but open group meeting. And by that time, I didn't have the answer. But then thinking that and having more like thought on the question, the answer wasn't that very simple. And actually the answer is very complex. I'm very happy to have this collaboration with Colin Evans and Brian Belcher, and of course, leading this investigation by Toby. And the question became complicated because to answer how predictable a drought, we needed a system to predict drought, and we didn't have the system at that moment. And that made a complexity. But the years 2020, we have the first the first version of the forecasting for drought, and then the picture at the top showed that forecasting issue in September 1st and the forecast value for October 2020, and it's very much 2 months. Similar analysis on the figure. So brown color showed the dryness and wet color showed the wetness. And here I'm showing in the bottom panel the US drought monitor for that particular month, October 20 of 2020. And you can see how the drought intensity in the intermountain region match with our observation. So that was a winning figure and a winning analysis after so many years. And it didn't happen like overnight. So this is to advertise how complicated was the question. How complicated was the question? Because the answer to this question became complicated because one of the fundamental variables for like changing the pattern of drought is actual precipitation. And precipitation has a predictability range of only like 10 to 30 days. So my question at the beginning of the meeting will be say like, okay, predictability is also only like 10 to 30 days, but that's not valid because there are more complexity. For instance, when we assess drought, because there is like an interaction between the soil, or how much can be storage in the soil, or how much can be, for instance, evaporated from fluxes. So motivation was based on precipitation, but we know there are more complexity on this issue. So previous to doing the analysis of predictability of drought, we started studying the variability on drought in the Northeast. Actually, I bring all my ground from the Southwest drought, but drought in Northeast are more complicated and have more different features. And here I am showing the average of that particular drought in 1960. That is this from 1962 to 1966. And we can the center of the drought on the New York region and Pennsylvania region. And then just took the average and just make a time series plot we show at the bottom. So the variability on time since 1950 to the present of that time, 2016. And there you can see the inflation of the time series in 1965, which correspond to this event. And also we had other events, for instance, like this event here between 1985 to 1916. There are two two characteristics in this time series. One, there is a very strong inter-annum variability, which can be observed when the fluctuation up and down for the time series. And also, if you see the envelope here after the year 2000, there is a kind of low frequency variability. If we perform a spectral analysis, we are going to see that feature, something decadal and a strong inter-annum variability, which is in the range of about 2 years. And then we use that information later to build our forecasting tool, which we didn't have in 2016. So here I would like to show what is the forecast skill of the drought, And here I had two plots. One on the left, I see the old version, and one on the right is a new version. The old version use just the standard approach, something that is called BCSD, bias correction spatial degradation, is the most sophisticated approach at that time. And there we are using correlation. And correlation, we can say that high correlation, we have better matching between the forecasting and the observation. Here for the Northeast, we see that we have like values in the range of 0.3 around. So very low correlation when we see droughts at the 2 leak time months. So with 2 leak time months, it means like we are forecasting the second month of the after the initialization. But this is the important part. When we have our new approach, what we are calling these EMOs, for ensemble model output statistic, see how we change the patterns correlation, how we improve. Even we have to change the scale. We didn't cut it to 0.4 than in the old approach, but we expanded over 0.7. So we at New York, we are moving 0.3 correlation to 0.7. That was a very interesting feature. And now we say, okay, we had the tools to answer the question, how predictable are drought? And we focus in the Northeast. Now we have the tool, but building the tool took very long. But I had to say this, thanks to Toby and his mentoring and advising, we had the flexibility to fail. And we failed a lot. Before this, we failed a lot. But now we have the tool, we can compare with the old version and the new version, and we had a winning strategy now. With that winning strategy, now we can answer the question, how predictable are droughts in the Northeast? And now here on the left, I'm showing the new approach. So in the vertical axis, again, I had correlation, and then the x-axis had the leak time. So 1 month, and 2 months, and 3 months. So for the first and the second leak time, I had very much similar correlation value. But for the third month, the correlation dropped, which means my predictability skill only lasts for 2 months. The third month, I don't have predictability skill. And this time series here, so this plot here on the left is for the Northeast, which is the specific case of the question. We tested with different training periods, which is like the different color mean different stuff, and it doesn't matter. So the correlation of the third month failed, But there is something interesting here. There is a clustering here. It's a cluster for these colors, the green and magenta, which correspond to 25 years and 30 years. And there is a clustering here in red and blue for 15 and 20. Those periods of time are training, is the period of the training of the data set. So what happened is a difference when I train the tool with 15 years to 20, and when I train it with 25 to 30. And this goes back with the beginning of the figure when I mentioned there is a 2 important components on droughts in the Northeast. There is one inter-annum variability, and the other is the decadal variability. So what is happening here? So the decadal variability is providing us with a little better information to improve the predictability in the months where I already have a good forecasting skill. That being said, is that happen everywhere? That happen in the same, and the figure on the right try to answer that. Is this happening everywhere? In the same case, no, it is not. Here, I'm not showing correlation, but here I'm showing skill score, where the value of 0.2 means like it's 20% better than the standard previous approach. And we have like for the Northeast, a big 20% better than the previous approach. But for instance, here in the Great Plain region, there is non-predictability skill score or even as negative. And the reason of this to happen is because the data set we use is the data of core resolution. But this core resolution is in the order of 2 degrees, which is about 200 kilometers. And we know the source of lack of predictability. And we can maybe improve the region, but we need an additional tool, you know? So going back to the original question, how predictable are droughts in the Northeast? I would say 2 months with the approach we are proposing. Now that we have explored this question about drought, we are moving forward in trying to do the same with another important component of the climate system. And this important component of the climate system is sea surface temperature. And sea surface temperature is important because regulate all the major process in the climate system. And actually we are now experiencing like a big transition from a cold temperature in the previous 3 months, potentially warm temperature in the tropical Pacific. And in the same way, this approach is trying to provide better forecasting skill, in this case for sea surface temperature. And then the figure here just show that is we transitioning for a standard approach, what I call a single model approach. We had this spatial pattern using correlation, and the lead time in this case is for 3 months. And the value here show that the skill score is centered on the Central Pacific. And when I added more sophisticated modeling simulation and averaged all of them together, I had very much no significant improvement. We got the same thing. However, when we start treating, when the technique we are proposing, you can see how the region span onto the northern latitude and the southern latitude. So I think the approach is showing like very promising results, and we are like trying to include this into a more like operational perspective of how we can use this information, for instance, for extended drought in other places like tropical region. So I think that is all that I have for today. I'm open for questions.
Great.
Mm-hmm.
Thank you, Carlos. And just, I mean, that's such exciting stuff with, you know, both seeing this and the Northeast drought predictability. It really speaks to your creativity and the quality of your work, that you can take something that, you know, when you joined Cornell in 2016, if you'd asked anyone how predictable is drought, they might have said, oh, up to 3 weeks, a month, maybe 2 weeks, 3 weeks. You've doubled at least the time scale on which we can make reliable predictions about drought. And now you're going to do the same with the SSTs in the Pacific, which affects global droughts. That's really cool. So I think we should do questions now, Q&A. Is that how you do it, Don?
That's how we do it.
Cool.
Okay.
Any questions? And we're a small enough group that we can just, I think folks can just raise their hand either like this or by clicking the reactions button to raise your hand like this. And take it away. Rob's got a question. Go ahead, Rob.
Okay. Well, I guess I'll start with this, with the most obvious thing, as somebody speaking as somebody who doesn't have much experience in knowing how one goes from the research literature into application in meteorological forecasting and application. How soon might it be before this is applied to the forecasting that's used widely? It seems like as soon as this is available, people will want to use it, or are people using it already?
I can take a stab at that, Carlos. I mean, I think our strategy is to roll it out cautiously, with our partners at NRCC, like our Digatano, because we want to have a, iterative and integrative approach where as we release these tools, we're not just like handing them out on stone tablets saying this is fact, but we have a dialogue with stakeholders and user groups that, might come back and say, well, these are really great and really helpful, but it's hard for me to interpret the maps as presented in this way, or hard for me to interpret the time series. So, but this summer we have plans to start with our quiet, public, but not super aggressive campaign of advertising, but we are going to start going live with this stuff this summer operationally. That's the plan.
Yeah.
And we've made it our lab goal. Like it's written on my whiteboard and tattooed onto my left arm. So got to do it.
And when you go public, what does that mean? Does that mean like posting like on a Cornell website, or does it mean actually like working with farmers directly, or working with people in the news? How does that happen?
Yeah, all of the above. So I think what we want to be able to do is just plug this into some of the existing outreach and data dissemination tools that NRCC already has developed. We can do it alongside them, or there's the Climate Smart Farming Initiative. There's a couple different sockets into which we could plug this, the work, and then yes, do it iteratively, get feedback. Take it slow. We're not trying to. We're not trying to follow the Uber model here of move fast and break things.
Also, I would like to add something like
Please,
something that is we are missing here, and we had a lot of conversation with Toby, is about the fact of spatial resolution. So we actually are moving into having more access to a spatial resolution on the results. Then we can be able to engage with as you mentioned, farmers, or going down scale on people can use the product. So that is the part and the component like we are working very intensively now, because the product is great. Just what it needs is, like, as Toby mentioned, satellite information, but that requires a lot of those kind of resources. We are trying to manage. Maybe something that happened during the summer.
And we should, if there's other questions, we can come back to this one, but I think people want, 100 meter, 50 meter resolution in their backyard soil moisture. But then it turns out, like, if you ask people, well, what, most people I've talked to anyway, who think they want soil moisture, turns out it's not really soil moisture. It's the impact of low soil moisture on some other system, on some plant or some ecosystem. And so that's what we're fine tuning. And so the tool, the metric that Carlos has picked is a really, I think, very clever one, because it's not, I wouldn't call it a one size fits all, but it's a very generic, generalized indicator that would be relevant to many different other variables.
Okay, Frank's got a hand up, and then Marion.
Yeah, thank you. Thank you, Carlos, for the awesome presentation, and thank you, Toby. I have a question. I was just reading a paper by Peterson et al. 2013 about epic pluvials. How does this fit into the epic pluvial mega drought scenarios?
Yeah, this is a great question. So, and as I'm sure you know, Frank, from the context of the U.S. Southwest and the Colorado River Compact, there was a period of time that was wet when they made the allocation agreements. That it was an anomalously wet period of time spanning several decades on which the averages that they used were based. And I guess we're on YouTube live and being recorded, so I won't say what I won't make my most dramatic version of this point. But what I will say is that I think New York State and New York City and the Northeast in general is very underprepared for the kinds of droughts that we might see in the not so distant future. And we tend to think of ourselves as being relatively buffered from the impacts of climate change because we have a wet climate and it's expected to get wetter. But I can give you countless examples from climate model experiments where, yeah, it gets wetter on average, but those dry years or those dry summers, those dry months or weeks when they occur could be devastating. And I absolutely think we are much more water insecure in the Northeast than we believe ourselves to be, because we haven't had to cope with that many droughts. Whereas in the Western US and California and the Southwest, because droughts have been part of the ecosystem, part of the management landscape for so long, you could argue that they're more well prepared. So I think we are vulnerable in ways that we do not fully appreciate, which is what's so important and exciting about Carlos's work, is to like at least start to lay the groundwork for using some of those tools. I don't think that was too politically unpopular of a statement. I tried to, I didn't give you timelines, I didn't give you numbers. I just think
Thank you.
my opinion from what I have seen is that we are not prepared.
Appreciate it. Thank you,
Okay,
Toby.
to Marion next.
Yes. Do you see any impact of the El Nino, La Nino cycles on this work?
Oh, in the Southwest for sure. And this year is really weird. It's the opposite signal of what we normally expect. But I'll let Carlos and Frank talk about that, because it's weaker in the Northeast, but in the Southwest and the Western US, absolutely.
Yeah, so just to answer your question, Marianne, in the Southwest, so in the past few years, we've had La Nina. And so, but we had more moisture than usual. During La Nina years, we have dry years, but we've had about, I think, 13 atmospheric rivers this season hitting the West Coast. So we've had a lot of precipitation this year. And we are coming up to an El Nino season coming
That's
up.
right.
That's the prediction. And that's the prediction is going to be that we're going to get a wet winter as a consequence, but we don't know. That's, yeah.
Yeah, I mean, it's like 30% of the variance, or yeah, not quite that much. In the Southwest, you think about like 30% of the time, El Nino would be linked to a wetter winter and La Nina would be linked to a drier winter. But there's that other 70% of the time, right? And so this last year was one of those examples where we just don't fully, there's lots that we haven't figured out. It's humbling. It's exciting. It means there's lots more work that we need to do and have to do.
Yeah, it's very exciting time, because we are not still in El Nino phase, like mathematically, because the Nino 3.4 is still like in a neutral, but El Nino 1.2, which is the area close to the coast of Peru, has been like 7 degrees over the average like climatology, and that little region has been producing a very extreme precipitation in the coastal region in Peru. Have been destroyed everything, roads, have been destroyed crops, everything. People is under very like intense pressure, you know. People lost houses, you know. It's been very dramatic. I've been following the news, and yeah. So now people is preparing for the full phase of El Nino that potentially happening on December of this year. And that in connection with the seasonality of the region, where the maximum is in March, might be a second very wet summer for them. Yeah.
And Carlos, that you said 7 degrees, that's Celsius, right?
Yeah, Celsius, yeah, 7 degrees Celsius.
And that is bonkers. Like, I can't express how just extreme of a sea surface temperature analogy and anomaly, excuse me. It's like, it's wild.
It is it is very bad, and a lot of people are going to agree that now it's like the connection with the global warming or the whole planet is happening. You know, the Nino is behaving as a superposition of two different warmings: the natural variability of the Nino and the warming of the planet, which is like we are seeing that. It's not like the climate change projection. It's not. We are out of that phase already. We are like sensing that. So that's critical.
Yeah, this next El Nino cycle is supposed to be probably the hottest records that we've ever had coming up.
Yep. Yeah, it's like every El Nino year tends to be the hottest year on record, even though things are hotter on average each decade. There's variability, but the major contributor is that El Nino. It's like the heat gets stored in the Western Pacific Ocean, and then boom, it gets released all at once or relatively quickly. And then, you know, that's temperature. And then you think about, okay, well, temperature gets like, when there's a temperature anomaly, it's sort of easier to spread it around evenly throughout the world. Whereas when there's changes in the structure of the tropical Pacific, it's like, you think of it as like a fire hose, and you're moving the position of the hose, and you're moving the ripples in the hose. And suddenly the places that used to get lots of precipitation are in a drought just because it's 30% reduction or 60% reduction, but that precipitation is going somewhere else. And those places where it's going are just getting hammered with rainstorm after rainstorm, atmospheric river after atmospheric river. And so, yeah, those little aberrations to the flow of moisture through the atmosphere have huge impacts for us on the ground. And this next one, absolutely, I expect to have big impacts all over the world.
Does it impact your lead times on those graphs?
Well, this is actually, I would say this is one of the, I go like Carlos answered, one of the challenges that we didn't have a good, strong ENSO signal in the Northeast to work with. So we weren't guaranteed to get as long of a lead time. So what makes Carlos's work really significant was that he had to do it without El Nino. The Southwest,
Yes.
they have the advantage of having that El Nino lead time.
Thank you.
And Rob's got another question.
Now, this will go back to something that you said, Toby, that, and I think you were trying to veer away from any extreme predictions, but you mentioned that there might be drought in the Northeast that people haven't really taken into account. And it reminds me that about 5 or 6 years ago, a colleague who I think she did her Catalina Stuf in the Netherlands had done her postdoc work at Cornell and had returned to the Netherlands. Her specialty is on basically preparing for wildfires, and I remember her saying, what are people doing about the possibility of protecting against future wildfires in the Northeast? And at that time, I asked around a little bit, and it seemed like I couldn't really get anybody's attention because opinions seemed to be that, well, although there's going to be climate change here, we're not expecting that level of drought. But it sounds like you're actually saying maybe that's not the case. So anyway, to get to the point, do you foresee a time that the Northeast might see some of the wildfire problems, maybe a few decades from now, that we're seeing in other parts of the world?
I'll give you my official answer.
Okay.
You can read into it what you will. I think the risk is not zero in any given summer. The dynamics of wildfires in the Northeast are a lot different than the dynamics of wildfires in the Western US. And because we have relatively small samples to work with in the Northeast, there's a lot of uncertainty. But I think we're going to learn a lot in the next decade or two and reduce that uncertainty, because we are going to probably have more observations of those dynamics. And we'll also have better models, and we'll have better understanding of soil moisture and the stresses and the kinds of triggers for those events. But if you look at what's happened in the Northwest, and this may or may not be an analog, right? And the dynamics are very different in the Northwest. But one of the important parts of the Northwest that we've seen is that, if it's an early spring, a warm early spring, vegetation can get going sooner, snowpack melts off sooner. That presents a very favorable suite of conditions in the Northwest and the Western US for big fires later in the summer when it gets hot and dry, because there isn't typically a strong summer soil moisture or soil, moisture recharge from the atmosphere. In the Northeast, we're lucky in that we get about half of our rainfall in the summer and half the rainfall. It's pretty evenly distributed among each season. It's a quarter in the winter, a quarter in the spring, a quarter in the summer, a quarter in the fall, approximately, depending on where you are. Those numbers are going to vary. So it's not the same, right? And so we don't really know what earlier spring, warmer spring means for fire risk in the Northeast, and that's a big uncertainty.
Thank you for explaining that.
For dodging the question.
It is. I found it interesting that we had fire warnings here in Western New York in the last few weeks, and there actually was I think on the order of 40-acre brush fire in southern Erie County a couple of weeks ago.
Yep, Pennsylvania had some brush fires just a few weeks ago, and Boston had Massachusetts, just west of Boston, had a few that that the fire towers reported. And so, yeah, it's we call ourselves the Emergent Climate Risk Lab for a reason. And that's that there's a lot of phenomena for which the number of observations is like 1 or 0. And they arise from coupled nonlinear interactions that we simply have never observed. And then we do, and we have like n equals 1. And what do you do with that? And so I think this drought northeast fire connection, even if we don't go down the route of the fire, the northeast drought connection is really an important thing to watch, because the dynamics are almost certainly going to change, because the timing of snowpack is changing, the spring warmth is changing, the growing season is changing. And yeah, it makes it very hard to predict. I guess the most likely prediction, if I was like, as someone pin you up against a wall, maybe Carlos, you disagree. If you disagree or agree, you should tell me. But I think going back to the fire hose analogy, it's sort of like we're cranking up the water pressure in the fire hose. We're increasing the volume of water moving through that hose, and it just starts flopping around more wildly. And so the variance I would expect to increase, both in terms of extreme precipitation and in terms of flash droughts and like high impact, short-lived droughts, and maybe even the prolonged ones as well. But especially the variance I would expect to increase. What do you think, Carlos?
Yeah, we are entering in a very complicated situation because we thought we have been observing natural variability, but we have a natural variability contaminated with the climate change. So we had a very interesting problem trying to separate the signals. And then the thing about the changes on the variability may seem just complicated, may seem we need like, we need more data, observational data sets. Satellite helping us, will help us a lot, but we also need ground observation and doing a lot of like correction on the data. A lot of understanding, I think, is missing,
Yeah, no, you make a good point too about data. I mean, it's so exciting too. Another really exciting area, not just the satellites, is that it's become so inexpensive to make indirect soil moisture measurements with low-cost sensors that can be connected via wireless. And so we are amassing just so much more soil moisture data than we used to be able to do. The problem is it's short term, right? It's 3-5 years at most. 10 years would be like a very long soil moisture site would be 10 years. And that just doesn't give you the same depth and breadth of understanding that like Carlos's drought atlases give you, because he can go back to the 1950s with them. So, yeah, it's an exciting time, but not for all good reasons.
Other questions? I have one if nobody else does. So I will ask. You're talking about being able to predict droughts instead of 3 weeks out, 3 months out, or something along those lines. Is there an analogous change in forecasting that's happened in recent years that has filtered out to the farmers and the weather bugs and whoever else is interested in following along? So does that question make sense?
Are you asking if there's been like a breakthrough in forecasting in general, or if this is specific to Northeast drought?
In general.
No, I'd say this if you like plot the rate of improvement to forecast for other variables in other parts of the world, Carlos's work like jumps out by like at least 2 standard deviations as like a major leap forward. Yeah.
That's pretty cool.
Yeah.
That's pretty cool.
Yeah, and it can be applied for another different variables. For instance, we have been applying this for the onset of the spring initially, and then we are testing on the on sea surface temperature, and we having like similar tendency with different values, of course, but similar tendency of having a significant improvement on the predictability, which make us very optimistic on expanding the approach on different variables. Something of the key important is just the data set is important. Is something like, because all the approach is a database approach, as much data we have, the better predictability,
Yeah, and I'll go on a limb here and say something, and if I'm wrong, don't blame me, blame the sparkling water. But I would say that we are in what might look like historically some sort of like sweet spot of predictability, because we have so many observations and so many advanced tools, all the way onto like machine learning that we're starting to use now for forecasting, but even the more like conventional techniques and the really cutting edge stuff that Carlos has done, which is right on the edge of machine learning. I think we would probably have rebranded it. If we wrote the paper now, we would have rebranded it as being like a machine learning algorithm, but we didn't at the time necessarily, right, Carlos?
Yes.
I mean, but we have all these tools, we have all these models, we have all these techniques. They've come a long way. We've got a lot of data, and so we are making predictions of a system that we're starting to understand. But that system is changing rapidly. And so all of that knowledge about how it behaved in the past, each year becomes in a way like less useful. So we learn more, but it's less useful because the system's dynamics are unfolding differently from how they have for the last century and a half. And that makes it like right now, I think, is a sweet spot. In the future, it gets harder and harder. Now, maybe our tools will be able to keep up with that. I don't know. Looks like Brendan has a question.
Does.
Hi, thanks for all of your talks. It's great to hear about. I have a massively ignorant question to ask. So
we're all massively ignorant.
This is like a huge leap in the amount of lead time and very impressive movement of concordance between prediction and what happens, which is all really awesome. From the perspective of like other stakeholders, like what does this let people do differently? Like what like I'm sure there are benefits, but I don't know what they are. So like what does having an extra 3 weeks of prep time do if you are an apple orchard or like a water management person for various municipalities?
That's a great question, and one that we ask ourselves, I think. And one of the reasons why we want to partner with other organizations who have that more direct connection to the farmers and growers. And I would say that we sometimes don't know the answer to that when we have these breakthroughs. And it often boils down to just rebranding, just relabeling our axes, so that instead of using -1 and -2 and -3 for bad, really bad, and super bad, we put some historical benchmark in there. So like this is like 2016 bad, and this is like 1990s bad, and this is like 1960s bad. And when you put it in those terms, we're like, oh, I know what you mean. Okay, thank you. And so then if you can predict, if you can say with 60% confidence that it's going to be 1960s bad in 3 months, I might, not spray the apples this year. I might just, first of all, the pests aren't going to be as much of an issue because it's drier. I'm not going to have to worry about fungus as much, maybe because it's drier. So I'm just not going to spray because I don't have to spend the tens of thousands of dollars on pesticides and herbicides when I think I might lose half the crop anyway to a drought. That might be one. Now, this is just an sort of hypothetical example from growers that I've talked to. But that's the kind of choice that you might make differently, because all through the growing season, there are inputs, right? And if you look like at what are the total, I forget exactly the ratio for apples, but it's something like for every calorie of apple that's produced, something like half a calorie or 0.75 calories goes in. So there's like a ratio, it's slightly greater than 1 of energy in to energy out for apples. But all those, what is that energy in? It's fertilizer, it's pesticides, it's human labor, it's diesel or oil to move the equipment around. And so you would just reduce those inputs to try to save costs if you thought it was going to be a bad drought. Now, if you're an apple grower, you can probably tolerate a pretty bad drought better than maybe a corn farmer could.
Have you started talking to like CCE folk, or
that's part of this sort of network that we're starting to work with?
Part of,
but because, and I think going back to your point that it's a big leap forward, we do want to be careful and not oversell it. Like scientifically, it's a huge breakthrough, right? Carlos's work is amazing. Practically speaking, we don't want to oversell it, and we don't want to do it in a way that's like reckless or out of touch with the people whose lives and livelihoods are going to be impacted by the real decision. So yeah, absolutely partnering with CCE, partnering with NRCC, and doing it, gradually, iteratively, carefully, and meaningfully.
Thank you.
Other questions? Rob?
So I want to actually go back to Frank's talk, because there are a lot of interesting things that, like, as he was talking, I was thinking about taking dust samples and what that means for students and so on. And so, Frank, I was wondering, so if it's realistic that students could collect empirical dust samples, I guess what I mean is natural dust samples, or is it necessary for them to basically model what a dust storm and the dust sample would look like in their classroom, because it would take far too long, or there just wouldn't be enough material to collect?
Yeah, so that's a good question. In terms of the physical model that I developed using 2 plastic boxes, they're really engaged with that because they like playing with dirt, right? So I had them play with fine grain sediment, coarse grain sediment, compare the results, use water to moisturize the soil, and so they were really engaged with that. Now, using the dust traps, engineering the dust traps, it's either, well, the Institute for Tribal Environmental Professionals has done that in the past, but it takes time. There needs to be like a summer program or a academic year program where students actually engineer the dust trap, or another way is just for me to just give them the dust trap. Here you go, collect the data, collect the dust, and then once 3 months later, 3 months down the line, use deionized water to take out the dust from those marbles and from those dust traps, and put it into bottles so that I can take it back to the lab here at NAU and measure it, or maybe measure it there in class. We can actually use just a standardized one of those kitchen scales that measures how much cinnamon you need, how much cardamom you need for a recipe. We can use one of those, and students can actually do it in class. That would be my ideal situation, is to have students do the science instead of me taking their samples and I do that in the lab. I'd rather have them do it themselves in the ideal situation, so that they're actually doing real, they're doing everything. They're actually engineering the dust trap, they're collecting the dust from the marbles in the dust trap, and then measuring, actually decanting the water to get that dust from those bottles to measure the weight. And then the only thing they couldn't do would be the composition. There you would need a X-ray diffractor or X-ray fluorescence. So X-ray diffractor for mineralogy, or X-ray fluorescence for elemental composition. So those are the 2 things that students wouldn't have access to unless we had a handheld device, which does exist for XRF, but they're very expensive.
Yeah.
Other than that, yeah, that would be my ideal situation, would be to have a short internship program, just like the Saturday Academy that I ran for 3 hours. But instead of just one Saturday Academy, but having a 2-month academy on the weekends, or a continuous 2-week program, and having students engineer the dust trap. That would be the ideal situation.
Are there already citizen science programs where people can put a dust trap in their backyard or something and collect samples? Maybe they don't analyze them, but kind of like other forms of weather data collection?
Well, one of the data collection devices is a sensor. It's called Purple Air. It measures PM2.5 and PM10. So there's a map that citizen scientists can acquire and put that online. But it doesn't capture things that are greater than 10 microns. So we're kind of at a loss there. You can capture particles that are from a forest fire, from air pollution, air pollutants. But in terms of dust, it's challenging unless you use a dust trap, which takes a lot of work to engineer, and then capturing that. But the propyl air can do it. I think Toby talked about the egg that measures the air quality as well. So I haven't used that one ever. I've used the propyl air sensors, and I've used the ACES, which is a pump that it's a device that pumps air out of the atmosphere and measures the air quality using cartridges. So that's one of the professional devices that I've used before. Last year I used it at Hoopa, California, with the Hoopa tribe there. The propyl air sensor, or also the smoke and air map, that's by the EPA. So if you go to the smoke and air, if you just Google a smoke and air map, that's a collaboration between the United States Forest Service, Purple Air, and the EPA. They post the air quality results online, and you can actually see the maps. And when, just as an aside, when I was in New York back in 2021, I was standing at the roof of the, I don't know if you've ever been to the International House, but it's just near Columbia University. I used to live there. And the air quality was hazardous. And a lot of that air was coming from the west, the western fires. I don't know if you remember that, 2021.
July of 2021.
Yeah, I couldn't breathe because even I was right next to the Hudson River. All that fire that was generated in the west came over because of the mid-latitude westerlies, and just, I can't breathe. So yeah, so something that happens far away has an impact on the other side of the country because of the mid-latitude westerlies. So that's one of the pages in the Earth Science reference tables, where students have to learn about the different, they have to learn about the Hadley cells, the Ferrel cell, and the polar cells, and they can see where the wind is going to. So that's one of the, formative assessments that that I gave my students at the time. Like, well, there's a lot of fires. Let's go to this website, ncweb.org, and the incident website, where you can see where the incidents, the incidents of wildfires are occurring. And so they saw a lot of the fires occurring on the West Coast that were impacting their communities downwind in New York City.
Amazing.
So yeah.
Other questions? Interesting session. Thank you very much. I'm going to put the.
It's been amazing. Thank you. Thank you all.
Yes.
No, thank you. This was fun. And it's good. It's always good to be reminded of the cool things that the people I work with are doing.
Yes, yes.
The SST stuff that Carlos showed at the end, like that's the next. What Carlos is hinting at. I don't want to oversell it, especially because it's like on YouTube and everything. But what Carlos is hinting at there at the end, I'll just leave you all with this. Suggests that his successes in the Northeast can be expanded to the global context. And so when you see him in the future, you'll know you saw it here first.
We'll say we knew him when.
Yeah.
We'll
Thank
have
you,
you
Toby.
back in a year to get an update.
Yeah.
And
Thank you very much.
Coming up, we've got in May, we've got 4 different online events to Science in the Virtual Pub, with 2 weeks from tonight having Deb Horde talking about science filmmaking. 4 weeks from tonight, we'll have a panel of experts talking about the needed changes for the electric grid in our changing energy system and changing climate system. And in between those two, we'll have Marianne Krasny talking about her new book on May 16th, I think it is, yes. And the day after that, we'll have a listening session for the Climate Literacy Principles Update. And you're all welcome to join us for any of those. And thank you all for joining us tonight. And thank you for the great series of talks tonight.
Thank you very much. Bye-bye, everyone.
Thanks, everybody.
Thank you very much, everyone. Have a
Thank you.
wonderful evening.
Bye-bye.